We'll go through 2f and we'll see how we go with it. We may look at some of 2g, but basically f's going to be new, and then we look at some of g, I, and j, and it's sort of stuff that we've done before and that we're familiar with. Okay, so here's the factor theorem, and it follows on from the remainder theorem, right? We saw with the remainder theorem, you know, if p of a equals k, then k is the remainder when it's divided by x take k. That's what we saw from the remainder theorem. The factor theorem says if k is a 0, then x take k is a factor of p. If k is a 0, it means p of k equals 0. Right? That's what it means. If it's a 0, it means the whole function equals 0. And so if this is our polynomial, then it means we can pull x take k out the front, and that is a factor. And so if we can identify one of the zeros, we can pull it out the front straight away to factorise it. So here we have x take 3 is a factor of this equation. Find the value of a. So if x take 3 is a factor, it means, let's call this p of x, it means p of 3 equals 0. That's what it means. It's a factor, so you put it in, it's a 0, and so that means when we put the number 3 in, it's going to equal 0. So let's go ahead and crunch this. So we'll have 27, take 9763. We've got minus 45 plus 3a is 0. So we'll have 45 is 3a, we'll have a is 15. Alright, so that's an easy application of the one. In question 2 here, we're going to have a beautiful collection of both the remainder theorem and the factor theorem. So we're going to be applying both here to go ahead and solve it. So we need to read the question carefully as well, because this is going to give us some pointers as to how to solve it a bit later on. P of x is a real cubic polynomial. It's a cubic. All right. When p of x is divided by x take 1, the remainder is 35. And when it is divided by x plus 2, the remainder is 80. Find the values of a and b given p of x can be written like this. Okay, so we're just going to use the remainder theorem straight away. Firstly, we're told when p of x is divided by x take 1, the remainder is 35. That means p of 1 equals 35. Okay? What is p of 1? I'll do p of 1 a bit slowly, but what you'll see is we're going to have q of 1 times 1 plus 1 take 2 plus a plus b. Okay. The important thing going on here, 1 plus 1 is 2, take 2 is 0. So we have a 0 here, and we have q of 2 times 0, so q of 1 times 0, so that part disappears. And we're left with a plus b equals 35. Alright, so we've used that first piece of information. Let's use the second piece. When it's divided by x plus 2, the remainder is 80. So we'll go p of minus 2 using the remainder theorem. P of minus 2 equals 80. So that means now when we put minus 2 into the equation, it's going to be 80. So if we put minus 2 in, we can see we're going to have 4 take 2 take 2. Alright, so 4 take 4 is 0, that's going to 0, that's going to 0. And so we're left with minus 2a plus b equals 80. Alright. Now when presented with simultaneous equations, if we can use our calculator, I think we should, just because it's faster, requires less sort of brain processing power that we can utilise elsewhere. So I'm going straight to my equation solver, simultaneous 2 unknowns, and I'll put this information in. 1, 1. I mean, this would be reasonably easy to solve together because you can see you just add the equations, but let's not waste time. Minus 2, 1, 80. I've got a is minus 15 and b is positive 15. Okay, so we've found those values of a and b. Alright, we're told here we're going to use the factor theorem. B. So that's the answer to part A. In part B, x take 2 is a factor of p of x. Show that q of 2 equals minus 5. Okay, if x take 2 is a factor, what that means is p of 2 is equal to 0. Okay, so let's put p of 2 into the equation along with the values for a and b that we've discovered. So that's going to be q of 2 times 2 squared plus 2 take 2. Plus, we've got a is minus 15. Minus 15 times 2. And then b is 50. We know p of 2 is equal to 0. Alright, and then we're just going to solve this for q of 2. We're treating this as a variable. We don't know what it is, but we know that this sum and product here goes to 0. So let's figure it out. We're going to have q of 2 times, we've got 4 plus 2 take 2, that's just 4. Q of 2 times 4, and then here we've got minus 30 plus 50. We'll just solve this like a linear equation. That's going to be 20. So we've got q of 2 times 4 plus 20 is 0. Q of 2 times 4 equals minus 20. Divide both sides by 4. Q of 2 is minus 5. And that's exactly what it asked us to show. Alright. Given the leading coefficient of p of x is 1, show that q of x is x take 7. The leading coefficient of p of x. Alright. P of x, we're told, is a cubic polynomial. Now let's just do some revision when we're talking about a polynomial, what we mean by coefficient, what we mean by degree. Alright, so if I have ax to the power of n, this is the coefficient, it's the number in front of the variable. This is the degree. Alright, that's what we mean when we refer to the degree, it's the power. Now we're told the leading coefficient is 1. The leading means the coefficient to the variable with the highest power. Okay? So we know it's a cubic, so we know when we expand this out, the highest degree is going to be x to the power of 3, and we know that the number in front of it is 1. Okay? So that means q of x has to be a linear factor. Has to be, because we have a linear times a quadratic gives us a cubic. So q of x has to be some linear factor, right? Ax plus b. But then we know the coefficient of the x to the power of 3 term is 1. Okay, so this has to be 1. And I won't use b because we've already got b's in there, so I'll use d. Alright, so we know this q of x factor, so here we have part c, this q of x factor has to be something like x take d. Okay. Alright, are we clear how I've come up with that? Q of x equals x take d because it's a cubic and the leading coefficient is 1. Alright, the next part, what we're going to do is we're going to use the information from the previous step, which is that q of 2 equals minus 5. Okay, that's why we did that. Which means when we put the number 2 into q, where the x is, we're putting 2 where the x is, because that's an x value, it's going to equal minus 5. So let's do that. So we're going to have q of 2 equals 2 take d equals minus 5. Alright, you can see if we're going to solve for d here, we're going to move d over this side, and minus 5 over here, we'll have 2 plus 5, we'll have d equals 7. Therefore, q of x is x take 7. Okay, last part. Hence, find the polynomial in expanded form. So this is going to be nice and easy. Come over here and do it over here. So we've got the polynomial of x is a cubic polynomial. It's q of x times the quotient, which is x squared plus x take 2. And then we have plus, take 15x plus 50. So we're just going to expand and collect like terms. We're going to fully expand this cubic polynomial. So we will have x to the 3 plus x squared take 2x. Take 7x squared. Take 7x plus 14. And then take 15x plus 15. And even then, might be that one here. Take 15x let's collect x to the 3. We'll have take 6x squared minus 2 minus 9 minus 24x and plus 64. Wonderful. Alright, so there's, like, the factor theorem starts with some pretty basic ones like we started with, but then they get into some more complex applications where we're collecting the techniques that we've explored already. So let's have a go at the factor theorem. I'm going to come around and see how we all went with the